Hello friends, welcome to session 11 of our series on foundational concepts in AI. This session is going to be about bias variance decomposition, noise and overfitting. Now the topic of bias variance decomposition can be studied at two levels. You can either look at it in a generic sort of a high level broad sense, or you could really do a deep dive because it is a complex topic. We will do both. Okay. Having a general high level understanding of the topic will allow you to blurt out some buzzwords if required in a job interview, particularly in India. Okay. And having a deeper understanding of the topic is critical for any serious student of this subject. So we are going to be doing both. Let's get started. There is a lot to cover today. Okay, a quick recap. We said that there are two separate analytical tools or theories for analyzing Eout, the out of sample error. We've spent a couple of lectures looking at the PAC theory, or the probably approximately correct theory, which relates Eout, the out of sample error, to In, the in sample error, right? And this was an equation that we established would hold with a probability greater than 1 minus delta, Eout being less than In plus another quantity that is a function of these parameters. Okay, so we've done that in the last couple of lectures. Today we are going to cover another theory called the bias variance theory. The bias variance theory is another way of decomposing Eout, and it decomposes Eout into a bias error and a variance error. Okay, so out of sample error equal to bias error plus a variance error. And then our objective, of course, is to try and control both of these error terms. That is what we are going to be doing. Motivation. Important to understand the motivation for learning the bias variance theory. Okay, why do we need yet another theory when we already have the PAC theory at our disposal, and it assures us that by increasing n, the number of training examples, you can bring Eout as close to In as you want, right? So what is the motivation for learning or studying the bias variance theory? Let's look at this framework that we've been using for the last several lectures, and to quickly recap the blocks over here, we have the target function f that maps the input space to the outputs y. Okay, essentially every input xi is mapped to an output yi, and the inputs are governed by a probability distribution p. The same probability distribution also governs the choice of your training examples, and you have n of them. You have n training examples. You have a hypothesis set that contains the different hypotheses that are available to you, and the job of the learning algorithm is to select a final hypothesis based on the training examples that is as close to the target function as possible. Okay, so remember the word final hypothesis. We are using the word final hypothesis indicated by the letter G, and the final hypothesis is the one that is determined by the learning algorithm to be the closest to the target function f out of this hypothesis set. So to recap, I want to spend a minute here. G is that age that is closest to f, and we are denoting it by a separate letter G. Okay, so G could be h3, it could be h2, it could be h100, whatever it is, but it is the function of the hypothesis set. It is a function from the hypothesis set which is the closest to the target function f as determined by the learning algorithm on the basis of the training examples. Okay, so keep this word in mind, the final hypothesis G, and remember what that is. Now, more or less in the last few lectures, we have looked at, the three primary blocks in this diagram separately, right? I mean, the three key blocks over here are, of course, the training examples, the hypothesis set, and the learning algorithm. So, and we've looked at them pretty much individually. From a point of view of the training examples, we've looked at the VC bound, right? We've looked at the VC bound, and we've seen that increasing the number of training examples is a solution to reduce Eout, okay? As long as, of course, the hypothesis set had a finite VC dimension. But you could make the quality of your output better and better by taking more and more training examples. We were assured of that in an earlier lecture. We've also looked at the hypothesis set, and we've spent time trying to capture or trying to evaluate the complexity of hypothesis sets, the complexity or the capability of the hypothesis set with something called the VC dimension. We did it in the context of binary classification, but the idea was essentially to relate it to the number of dichotomies that you could create. And we saw that VC dimension had an inherent relationship with the number of parameters that are available to the functions in the hypothesis set. Okay, so the degrees of freedom. And the degrees of freedom, we said, were a way of evaluating the complexity or capability of the hypothesis set. We've looked at the hypothesis set in that context. We also looked at learning algorithms in their own right. And when we talked about the linear models, we said that the learning algorithm could be configured as an optimization algorithm, where we defined a mean square error, an error metric such as the mean square error that could be minimized, and that minimization happened iteratively, for example using the gradient descent algorithm, right? So we looked at the gradient descent algorithm. The bottom line was that the learning algorithm was configured as an optimization algorithm. The learning problem was configured as an optimization problem, where we optimized the mean square error, some sort of an error metric that yielded the final hypothesis, okay, the final hypothesis. So we've looked at these three blocks individually so far. To me, the biggest reason for studying the bias variance theory is that it allows us to investigate the interplay between these blocks, okay, how well these blocks work together with each other. Now, imagine you are putting together a football team or a hockey team, right? You would look at the quality of the individual players, but you would also look at how well they combine with each other, because they have to combine well to actually deliver results, right? So how well these blocks work together in tandem is an important consideration while designing the overall system. We cannot look at them in isolation. And that is what I meant by interplay between blocks, their compatibility, how well they work together. And like I said, the primary reason for studying the bias variance theory in my mind is that it allows us to investigate the interplay between the blocks and evaluate how best they can work together, right? So that is the motivation for studying the bias variance theory, and that is the reason why this theory is so important. Okay, so here is the outline of today's lecture. We are of course going to study the bias variance theory. We are going to study the bias variance theory because that is the topic of today's lecture. And like I said, it provides a unique perspective on interplay between the blocks. So that's the important reason for studying the bias variance theory. We are also going to be talking about something called the noise, okay? Noise is an unavoidable factor in any practical scenario, okay, and therefore its impact needs to be understood. What is noise and how it impacts our calculations, okay? It is something that in practical scenarios cannot be avoided, and therefore it is important to study noise. We'll factor this into our calculations. And we are also going to be talking about the idea of overfitting. Now, we talked about overfitting and underfitting very briefly in a lecture, a couple of lectures ago. And these are ideas or concepts that are actually related to bias variance. Okay. And understanding overfitting and underfitting will actually shape our approach to trade-offs and choices that we have to make. So that is why overfitting is best spoken about in the context of BV theory. BV for bias variance. Okay, important note. This lecture deals with scenarios involving insufficient n, okay, and that is usually the case either by circumstance or by choice. Let me explain what I mean here. Now, some of you may say that we've already looked at the PAC theory and the solution to all learning problems lies in simply increasing n. Right? So no matter what the VC dimension of your hypothesis set is, no matter what your problem is, just throw more training data at the problem and you will eventually end up with a good system. Right? So increasing n is a solution to all our woes. That's what the PAC theory would suggest. So why are we even dealing with situations involving insufficient n? Okay, inadequate number of training samples. Well, in practical scenarios, insufficient n, having inadequate number of training samples, is something that happens by circumstances or by your own choice. Now, what do I mean by circumstances? Well, in many scenarios, you may have finite training samples. You are not at liberty to ask for more training samples. This could happen. I mean, you are given a fixed number of training samples and you are supposed to design a system using those many training samples only. So that's one circumstance that may involve insufficient n. Or by choice. What do I mean by choice? Now, whenever you are designing a practical system, you do not know the complexity of your target function. You do not know the complexity of your target function, and therefore, usually you are trying to look at more and more complex hypothesis sets to mimic your target function. And as we've studied in the PAC theory, more and more complex hypothesis sets require higher and higher n, and pretty soon you would hit a stage where your n is insufficient, right? So that is what I mean by saying by choice. And then there is another factor in over here, noise, right? So this noise that we spoke that we are going to talk about also leads you to a situation where your n may not be sufficient, right? So insufficient n is a scenario that you are often going to run into in solving practical problems, and therefore this entire lecture is built around the promise of having insufficient n, inadequate training samples. You do not have the option of saying just give me more training samples, right? Okay, so that's important to keep in mind. Okay, let's get started with the main topic of today's discussion, the bias variance decomposition. Okay, the bias variance decomposition decomposes the out of sample error into a bias error and variance error. Okay, and now let us understand at a high level, at a generic level, what these two are. Okay. The bias error relates to the question, how well can best G in H approximate F? Okay. How well can best G in H approximate F? You have a hypothesis set which has certain hypotheses in it, and probably there is a best G over here, your final hypothesis. How well can that G approximate F? It may not approximate F closely, and the error that results from the best G not being able to approximate your target function F very well gives rise to what is called the bias error. Okay, this gives rise to bias error. The variance error, on the other hand, relates to the question, how well can we identify the best G in your hypothesis set given specific training data? Let me repeat. These are important to understand, so I am going slowly, right? how well can we identify the best G in H given specific training data? Now, in any situation, you are going to be given specific training data, and given that specific training data, how well can you identify the best G in H that is closest to F? You may not be able to do that because of specific training data, and the error resulting from that is known as the variance error. Okay. Now, you can imagine that a more complex edge, a more and more complex edge, a more and more complex hypothesis set will allow you for a better approximation of F, right? So, as H becomes more and more complex, you could come closer and closer to F. There might be functions in your H that are closer and closer to F, but simply the fact that H has more complex functions is going to make that best hypothesis which is closest to F harder to find. Now, this is a concept that may be a little tricky to understand, and we'll look at it in some detail, right? So, a couple of other the phrases or terms that are used. Approximation error happens because a good approximation to F may not exist in F, and approximation error is essentially the bias error, and some other terminology that is used for variance error is the generalization error, and this happens because of inability to find the best approximation within H based on given data. So I am just throwing some terminology here in case you hear these words. I want to make sure you know that they are exactly bias and variance. Approximation error is bias error, generalization error is variance error, right? And let us I mean, this may sound a little odd, especially the variance error. So let me give you an analogy, a shopping analogy, right? Imagine that you're shopping for a particular dress, okay, a particular very specific type of a dress, and you go to a small shop, right? You go to a small shop, and if the shop doesn't have too much variety, if it is a small shop, you're unlikely to find exactly the dress that you're looking for in that shop, because simply that particular dress is not available in that shop. It's a small shop. The difference between the dress that you are actually looking for and the best dress available in that small shop is the bias error. Okay, and that error happened because simply the shop was small, it did not have the dress that you were looking for, and you ended up having to pick an approximately close dress to it, and that error, that difference is the bias error. Okay. Now consider a scenario where you entered a very large shop. Okay, that very large shop had exactly the dress that you were looking for, right? But it was an extremely large shop, and for a variety of reasons, perhaps the advertisements or billboards that were presented to you when you entered the shop, or perhaps because of the mannequins that were put up, or perhaps because of what the salesperson was telling you while you are going about your job, you ended up selecting a dress that was not exactly what you were looking for, but somewhat different from what you had set out to buy in the first place. Okay. Now, this may seem odd to some people, but any experienced shopper will tell you that it is quite possible to go into a large shop with something in mind and walk out with something that is different. And that happens because of the data being presented to you, namely the billboards that you see, the advertisements that you see, the conversation you have with the salesperson, and so on and so forth, right? So that would be an example of a variance error. You walking out with a different dress from what you wanted in the first place, but not being able to zero in based on the data that was presented to you after you entered that large shop, right? So that is the variance error. Now, why a similar thing happens in learning is what we are going to discuss in this lecture. Okay, But broadly speaking, bias error and variance error relate to these two different ideas, and your Eout, your out of sample error, is a combination of this bias error and variance error, right? I'll repeat because this is important. Bias error pertains to how well can best G in H approximate F, and it relates to the limitation of your hypothesis set, right? And the variance error, on the other hand, relates to the question how well can we identify the best G in H given specific data. So variance error happens even in circumstances where your H had complex enough functions, but purely because you were given specific training data, you ended up with a function different that is removed, or that is not exactly identical to the target function that you were seeking, right? So that's the shopping analogy, and that's what bias variance mean at a high level. Okay, a quick recap of some terminology that we had run into a few lectures ago: overfitting and underfitting. The ideas of overfitting and underfitting are closely related to bias and variance, and that's why I'm bringing them up right now. So overfitting is when your selected hypothesis tracks the patterns in the sample too closely. Okay, this is what we had said a few lectures ago. And underfitting is when your selected hypothesis does not capture the patterns in the sample as much as it should, right? So overfitting is when you select a hypothesis which tracks the patterns in your inputs training samples very closely, and underfitting is when your hypothesis does not capture those patterns in the sample as much as it should. Okay, now these ideas are related to bias and variance respectively. Okay, overfitting overfitting is when you have a large variance error, and underfitting is inherently related to scenarios where you have a high bias error. Now, it's very clear that these definitions that we've put out over here, these descriptions that we've put out over here, are subjective, right? I mean, we've used like words like too closely or as much as it should, right? So these are of course subjective terms, and we need to sort of quantify them a little bit moving forward. And the other question that you would have in your mind related to, of course, quantifying those words is, how do you know if you're underfitting or overfitting? So that is something that we need to address. But I want to bring in overfitting and underfitting over here because they are related to variance and bias respectively. Okay, let's move on to an illustration. Let's move on to an illustration of the ideas of overfitting, underfitting, and bias and variance. Like I said, I had promised you that we would do a high level generic description of these terms before we dived into the details. So let's look at an illustration that you may have seen elsewhere as well. Now, this is an example of underfitting. Let us assume that these points are the data, right? And your training data actually was just the brown samples. Your blue samples were out of sample data. Your brown samples were your training data. And your hypothesis set was basically straight lines or linear functions. And given this training data, this was the best hypothesis you could find that minimized the error, let us say. Now, as you can see in this example, you would have a fairly significant in-sample error and a equally significant, if not slightly more, out-of-sample error. Now, it's from this diagram, it's immediately clear why this error happens. The data, the pattern in the data is too complex, and that complex pattern simply cannot be captured by a hypothesis set that contains only straight lines or linear equations. And that is the reason we have these errors. We have these high errors. So this is an example of high bias and low variance scenario. So underfitting essentially relates, or gives rise to a high bias error component, and it also gives rise to a low variance, which we will see why subsequently. On the other hand, you can have a scenario of overfitting. You can have a scenario of overfitting where I have hand drawn a complex curve that passes through all of these training points, right? All of these training points. And now you can see that my in-sample error is going to be pretty small, whereas my out-of-sample error may still be large. Okay, so this is the scenario where my hypothesis set had complex functions. I did a pretty good job of nailing the training data that we have, but we still had a large out of sample error, and this is what we call high variance. It had low bias because our hypothesis set did have complex functions. So this is an example of low bias, high variance, and this is exactly what is called as overfitting. So now visually you can see what underfitting and overfitting are, and you can see how they are related to bias and variance respectively. You could also have something in the middle. Here what we have done is we have passed a second order function through the training data that you had available, and this results in a moderate or a low, you could say, in sample error and a moderately low out of sample error. And this you could say is an example of low bias and low variance. Now I am again using terms like low and high, and these are relative. I mean, low and high relative to what? Well, low and high related to each other. Here you have low bias, low compared to the bias for the underfitting case, and here you have high variance, high relative to the variance over here. Okay, and this is sort of in the middle, which is why it's moderately low sort of bias and low variance. So here you are better off not actually nailing the individual training samples, but sort of choosing a via media. A via media means a polynomial that is not as complex as in the overfitting case, not as simplistic as the underfitting case, but a polynomial of second order that does a reasonable job and results in a fairly low in-sample and out-of-sample errors compared to the extremes. So this is underfitting and overfitting. The terms are relative, low and high are used in a relative sense, and visually this is what is happening. The same applies for classification as well. I mean, we've in the earlier slide, we looked at regression, to be clear. The same thing happens in the case of classification as well. If you are talking about, for example, binary classification, if you do a linear classification, this is like a simplistic type of a hypothesis set, which results in high bias and low variance. Your in-sample error could be large, your out-of-sample error could be correspondingly large. In the case of overfitting right here, you draw a fairly complex curve which results in a very low in-sample error but a significant out-of-sample error. And this is again low bias, high variance. Or you could have a second order polynomial like we did on the earlier slide that sort of gives a relatively small in-sample and out-of-sample compared to the two extremes, right? So low, high are comparative terms. I have given you 3 examples, 2 on the extremes and 1 in the middle to make the point. But this is what the broad idea is. In a generic sense, this is what underfitting and overfitting means, and this is how it relates to bias variance respectively. Okay, great. It is now time for us to formalize everything that we've just discussed in mathematical terms. So we have a pretty good idea broadly of what bias variance are, but now we have to capture them in mathematical terms. So my next few slides are going to be mathematical slides, and they will capture the essence of bias and variance in mathematical terms. Now, in the last few lectures, what I have done is I have postponed all proofs to a separate lecture which is going to come later on. But the derivation of bias variance is so fundamental to our arguments that I am going to have to do it here. Okay, so the next few slides are mathematical and they will exactly tell you what bias and variance are. Now, the derivation that I am going to go over is in the context of solving the regression problem. So we'll have to do with real numbers, and we will use the mean square error as a metric, as the error metric. Bias and variance are after all errors, and we have to have some sort of a metric for those errors. And we are going to be using mean square error as the metric for our derivation. So let's get started. Okay. So, Eout, or out of sample error for a particular final hypothesis G, is equal to Ex, that is the expectation over X, that is the input space, of G of X minus F of X the whole square. I said mean square error. This is the square error, and expectation over X is essentially the mean square error, right? Because you are averaging over the entire input space. So this is Eout for the particular final hypothesis that your learning algorithm gave you. Now D is the particular data set. By data set, I mean the n training samples that were given to you. And it's of course clear that the final hypothesis that you end up with is going to be a function of that particular data set that you had that you had to work with, right? So G is actually a function of D, and I'm going to make that explicit by putting that as a subscript below the D. Okay, so GD essentially formally denotes the fact that this G, the final hypothesis returned by your training algorithm, is a function of that particular data set D that was given to you. It was probably implicit all along, but now it's time for us to put that down. We are going to ask the question, given any data set of n training samples, what is the expected out of sample error? Okay, so we are now interested in understanding what the expected out of sample error would be given some data set of n training samples. And why would you ask the question? Because you want to take the specific training samples out of the equation, right? So your final answers would depend upon the specific data set that you were given. But if you wanted to draw some conclusions regarding the hypothesis set and the training algorithm, the learning algorithm working together, you would have to remove the specificity of the data set out of the equation, and you would have to ask the broader question, what is the expected out of sample error given any data set? Why does the word expected out of sample error come into picture? Because there is a probability now associated with the data set itself, right? So your data set, the particular data set you take is now a random variable, and therefore there could be a expected value associated with the out of sample error for the training data set. The data set is the random variable, and therefore now we are talking in probabilistic terms in terms of expected values. That is what I am saying. This question is important for us to nail down how well the hypothesis set and the learning algorithm are working together. So I'm going to take the expected value over D, expected value over all possible data sets of Eout. And on the right hand side, I have a similar ED. Take the expected value over all data sets. Now notice that this thing in the bracket is always a positive quantity because it is a perfect square, and therefore the sequence of these two expectations can be interchanged. You remember how the expected values are found. I mean, these are essentially integrations for continuous variables or summations for discrete variables. And what I'm saying is that you can now interchange their sequence simply because this quantity here is always positive. You wouldn't have been able to interchange their sequence if this was not always positive. But because this is always positive, we are going to interchange their sequence and see what we have. So what we get here is expected value over D of Eout is expected value over X of this quantity right here. Now, expected value over X is something that we can easily relate to, easily understand. I mean, if you are looking at the mean square error, you obviously have to look at the entire input space and take the average over the entire input space to give you the mean square error, right? So this is fairly logical and we understand what that is. So for a moment, let us just focus on what is inside that expectation. Let us just focus on this quantity right here and see how we can simplify that. Okay, so this is what we are going to be dealing with. This is what we are going to be dealing with. This is what we want to understand. The first thing we are going to do is define a hypothetical quantity which averages the G over all possible data sets. So understand exactly what we are trying to do over here. We are going to define a quantity G bar. We are going to define a quantity G bar, which is essentially the average or the expected value over all data set of individual GDs, right? So understand what we are doing here. For each data set, we have a particular G, which is G of D right here. And for different data sets, we would have different Gs. What we are doing over here is taking the average of all of those. Expected value over D is essentially the average of all of those. And this is that hypothetical quantity. Why do I call it a hypothetical quantity? It's a hypothetical quantity because nobody is in real life, nobody is going to give you all of these possible data sets, right? You are going to have only one data set, but because you are looking at it in a probabilistic manner, let us define this hypothetical quantity, which is the average of all final hypotheses. That's the reason I call it average final hypotheses. In discrete terms, this is what is going to look like. This is what it's going to look like. I just put it here so that you exactly understand what this is. For each dataset decay, you have the final hypothesis and you are going to average them by adding them all up and dividing by k. You are averaging all possible final hypothesis to give you this average final hypothesis. That's what we are doing. And to repeat, this is a hypothetical quantity because nobody is going to give you all possible data sets. However, it stands to reason that this hypothetical quantity average final hypothesis is going to be very close to your best possible hypothesis in your hypothesis set. Why is that? That is because it has been determined by averaging all possible data sets. So all possible data sets have gone into determining G bar and therefore it is very close to the best possible hypothesis that is available in your hypothesis set. Why did I not say exactly equal to the best possible hypothesis? Because there is a little bit of a non-linearity involved. So understand this non-linearity. You are not being given all possible data in one go. You are being given data sets each of size n, one data set at a time, and you are averaging over all of those. So it stands to reason that your answer, if you had been given the entire data in one go versus taking n chunks at a time, is going to be slightly different. And that's the reason why I say it is close to your best possible hypothesis, but very close to it. And therefore it is a characteristic of our H, and we say that G bar of X, which is your average final hypothesis, is a characteristic of your hypothesis set because it is very close to the best hypothesis in your hypothesis set. Okay. So This idea of G bar is central to the bias variance analysis. So spend a moment, stop my video, go over it once again, over the last few minutes once again if you've not understood G bar. It is simply the average of all final hypotheses that result from taking all possible data sets to train your system, right? Okay. What I'm going to do is, in this quantity that we were trying to evaluate, I'm going to add and subtract G bar. The G bar, which was the average final hypothesis, which we saw in our previous slide, I'm going to add and subtract it from this equation. So I have GD of x minus G bar of x plus G bar of x. I can add and subtract the same quantity minus f of x, which was there earlier, the whole square. So this is equal to this, right? What I'm going to do next is simplify this term by using the formula for a plus b the whole square. This is my a, this is my a, this is my b, and I am going to use the formula for a plus b the whole square and take the expected value of d over that. So I have a square plus b square plus 2ab, right? Now notice that expected value over d of this term, the mixed term, the cross term, is 0. Why is that 0? Because expected value over d of GD of x is actually G bar of x. So you are going to be subtracting the same thing from here, from itself, and this is independent of d, and therefore the expected value over d of this is actually 0. Right? Of course, I'm assuming you know that expected value of a plus b is expected value of a plus expected value of b. That's exactly what I have done here, and this is 0. So the cross term is 0, and therefore what we are left with is actually just these two terms, right? Expected value of over d of this square plus this square. And therefore I can simplify it further and take the expected value of both terms separately. But because this is independent of d, I have dropped the ed which was over here. I have dropped it because this is independent of d. It does not depend upon a particular data set. So what we have here is the term of interest that we were dealing with is a combination of expected value over d of this thing, GD of x minus G bar of x the whole square, plus this quantity which is independent of d, which is G bar of x minus f of x the whole square. This is often referred to as var square x, variance square of x. This is often referred to as bias squared x, and therefore if you bring the expected value over x, which we had dropped for the previous slide, if you bring it back again, you end up with this equation, right? This equation is the same as this, except that you now brought the expected value over x back in, which we had dropped for convenience in the previous couple of slides. This expected value of x of var square x is referred to as the variance for short. It's not called variance square. In common terms, it's called variance, and this is called the bias. It's not called bias square in common usage. It's simply called the bias. So what you have here, this was your expected value over d of Eout of GD is equal to variance plus bias, where variance is this and bias is this. So this is the formal definition of variance and bias respectively. Okay. Let us now relate it to what we had done earlier before we jumped into the mathematical equations and see that it is pretty much the same thing that we have been talking about. Okay, so this is what we had. I missed putting the ex over here, expected value of x. expected value over x, which basically calculates the mean over all input space of this quantity, is equal to this plus this. And as we saw in the last slide, this is the variance and this is the bias. Okay, so this is the bias, this is the variance, and let us see if they are exactly what we discussed they were in general terms before we jumped into the math. Okay, now look at this variance. The variance is the expected deviation of your final hypothesis from the average final hypothesis. That is what this is, right? This was your data set. This is the final hypothesis that you got for your data set. This is the average final hypothesis. That is, you can say that is pretty much the best hypothesis available in your hypothesis set. And the expected value of the error resulting from a difference between the two is the variance. So variance is the expected deviation of your final hypothesis from the average final hypothesis. It's the expected value over d of gd of x minus g bar of x the whole square. Bias on the other hand is the deviation of the target function f from your average final hypothesis. So this is your target function f. This is your average final hypothesis, which is pretty much the best hypothesis available in your hypothesis set. And the difference between the two, like we said, is indeed the bias. Right? So these mathematical terms capture the essence of bias and variance that we have been talking about in general terms. Why is that? In the case of bias, this thing really answers the question. How well can G in H approximate F? Remember, this was the question that we had asked. What is the best possible G in your hypothesis set? And how far from the target function f is it? How well can G in H approximate f? That is the bias, and this is the mathematical definition of bias. Similarly, for variance, we ask the question, how well can we identify the best G in H given the specific training data? Remember, that was the question. And let me declutter this. If you look at this mathematical equation, you will see that that is exactly what this quantity captures. GD of x is the specific G you got for your particular data set. How different is it, or how far away from the best G in H is it? GD of x is clearly influenced by the specific training data set D. How far is it away from the best possible G in H? That's the variance, right? I think it would be instructive for you to just stop the video here for a couple of seconds, see this, absorb this, and be convinced that this is exactly what we were talking about in general terms, and these mathematical quantities exactly capture that. Now, I want to caution you. I mean, I said the generic terms, a slightly superfluous thing, etc., etc. Remember an important distinction, a theoretical distinction, which is often sort of lost in practical conversations, right? Variance and variance in particular is an expectation. So you cannot, it's the expected value of a random variable, which is different from the value that a random variable takes at a particular point in time, right? So you cannot say that for my particular hypothesis, this was my variance. That's not correct, strictly correct theoretical usage. Variance is an expected value of a random variable. It is not the value of the random variable at a particular point in time or in a particular manifestation. But keeping that very mathematical and theoretical difference aside, broadly speaking, variance captures the difference between the final hypothesis returned for particular training data as compared to the best hypothesis available in that hypothesis set, right? So That's what the mathematical definitions of bias and variance are. Okay. That brings us to, that's the first part of this lecture, getting a mathematical grip on bias and variance. And now let's talk about noise, which is an extremely important factor which is going to affect everything we do. So let us understand this idea of noise in a little bit more detail. Several lectures ago, when we were discussing linear models, we drew a diagram like this for a particular example. Remember, we were busy trying to model the salary, the relationship between salary and years of experience, right? So we had a table like this. We had gathered a lot of training data that said that for years of experience, for various years of experience, this was the salary. This was your training data, and we plotted it on a graph, and we tried to fit a linear model, assuming that the relationship between the salary and years of experience was a linear relationship. We tried to build a linear model to capture this relationship. S equal to my plus S naught, where y is the years of experience and S is the salary. You remember this from a long time ago. Now, at that time, some of you may have asked the question. Why is there, why aren't these, if we claim this relationship to be linear, why is there so much, deviation from the straight line? Why is there so much deviation? What is the reason why these points are sort of all over the place? They are broadly linear, but, why are they all over the place? Now, there could be several reasons. Reasons for the scatter. The first reason is that our target hypothesis does not lie in H. So in this particular situation, your hypothesis set was the set of all straight lines, linear equation, whereas your target hypothesis, which is the actual relationship between salary and years of experience, may not be linear to begin with, right? So the target hypothesis does not lie in H. The target hypothesis, which is the actual relationship between the salary and years of experience, is not a straight line and therefore does not lie in H. That could be one reason for this scatter. The other reason for this scatter could be unconsidered independent variables. There might be other factors that impact the salary, not just years of experience, and those are the factors that cause this kind of a scatter to happen. Now, you could say that 2 is, pretty much, you could fold it into 1. You could say that the independent variables, the weights associated with the independent variables are 0 in this particular hypothesis set. So these two are pretty much, I could argue that they are the same thing. But unconsidered independent variables and the fact that the target hypothesis does not lie in H because the relationship between salary and years of experience is not linear to begin with. However, there is another reason, and that is noise. Okay, noise. Noise is that unexplained randomness that you cannot explain and that is visible in your input-output relationships. It's the unexplained randomness in the input-output relationships in your data. That is noise. And it is often modeled in this way. So far we've said that y, the output y, is equal to f of x. And now what we end up doing to capture the idea of noise is we add a random variable epsilon, which essentially takes random values. So this is noise. It is unexplained. It is random. You cannot model it. Therefore, it is inserted here as a random variable. Now, in practice, most of the noise appearing in natural phenomena, typically the noise appearing in natural phenomena has a Gaussian or a normal distribution. It has a normal distribution, so there is an x bar, which is the mean, and then there is a standard deviation sigma, and the variance is sigma square. You all know this. we are going to assume that x bar is 0 and we will do it without loss of generality. So what we are saying is we are going to assume that the expected value of epsilon is 0. The variance is of course sigma square. And the reason why we can assume that expected value of epsilon is 0, the reason why we can assume that x bar is 0 is because we are saying if it were non-zero, we could simply fold it into f of x. So if x bar was non-zero, if the expected value of epsilon was non-zero, the expected value of epsilon could be made could be added to f of x, right? And then you would have the remaining epsilon would have essentially a zero mean. So without loss of generality, this is an assumption that we are going to make. That is essentially noise. Let us see how it impacts the framework that we have been using for so long. This is the framework that we have been using for many lectures, and now this framework is going to change. We are going to make an addition to it. Here what we have done is we have said that yi, instead of being equal to a function of x, we have said that it's going to be a function of x plus an epsilon, which is a random variable. Because epsilon is a random variable, you now do not have this deterministic relationship between y and x, but you now have a probability of y given x. Understand this. Every time you are given the same x, because of the random noise, you could have different values of y. So different possible values of y for the same x, and depending upon the distribution of this random variable, depending upon the distribution of this noise, you would have a probability distribution of y given x. The probability of getting some y given the same x. And this probability distribution is also going to impact your training samples. So your training examples are going to be determined by the probability distribution of x, and they are also going to be influenced by the probability distribution of y given x. Because y could potentially differ for the same x due to the noise. Now this does look pretty bad, right? I mean, so far we've been happily working under the assumption that y equal to f of x and it's deterministic, and it sort of gave us there was a certain simplicity associated with that. But now we are saying that everything is up in the air. Your data itself could be noisy, your training examples could be noisy, and you have to determine the final hypothesis that is as close to f as possible in the presence of noise. When you know that y could be corrupted by noise, your training examples could be corrupted by noise. So it definitely makes our task harder. Noise appears in every problem in real life. I mean, even if you were to think of, the language models that you train with a lot of text, you might run into text that is bad, that may have grammatical errors, and that goes into your training examples. So that is an example of noise. If you're taking readings, if you're taking physical measurements, every physical measuring instrument has a certain amount of noise associated with it. You can minimize it, but it will never go away. So noise is a fact of life. It complicates matters. It's a bad actor, but it is something that we have to deal with. And we are now going to see how this noise plays a role in our bias variance analysis. Great. I call it the bias variance noise decomposition. What we are going to do is we are going to replace f of x which we had all along, with f of x plus epsilon, where epsilon is a random variable whose expected value is 0, and epsilon is also independent of all the other quantities. Because it's a random quantity, it does not depend upon any other quantity, and therefore it is independent of everything else. Those are the two assumptions we are going to make. And with those two assumptions, I will leave this as an exercise for you. you can show that this particular quantity that we were dealing with, if you replaced f of x with f of x plus epsilon and made the assumptions on epsilon that I just spoke about, your variance and bias terms would come out as they are, plus epsilon square, which is the energy of the noise. Okay, epsilon square is the variance of the noise. So this is what you end up with, and I'll leave it to you to go through this exercise. It's not terribly hard. I'll put it as a question at the end of this lecture, but go through it, and this noise plus epsilon square will come right at the end. And what that means is that your overall Eout, your out of sample error is going to have this term sitting right in there. Just saying the same thing once again. This is your Eout of GD. We are going to be able to write it as variance plus bias plus stochastic noise. Stochastic noise because it's not deterministic noise. There is a randomness associated with it. You cannot model it, and therefore your Eout is going to be variance plus bias plus stochastic noise. Stochastic noise simply being sigma square. Understanding the impact of noise. Now this is an important one. Please pay attention to what we are saying. Remember this equation? I mean, this is what we've been dealing with. Again, I overlooked to put E of x over here. Variance, bias, noise, right? This is the deviation of your final hypothesis from your average final hypothesis, distance of the target function from your average final hypothesis, and the noise. And your G bar is this. Noise actually has a fairly bad impact. I mean, it's directly adding to your Eout. That's one thing. But noise also influences the specific GD if your data set was noisy, which we are now assuming is the case. So noise actually impacts GD of x in specific scenarios, and that is the reason why it is so bad. Okay, and I'm going to give you an example of this. Why can noise lead to poor GD? What's exactly happening here? This was the linear model that we talked about. Now imagine a few extreme conditions, right? I mean, imagine a few extreme conditions. In the presence of noise, the final hypothesis GD of x for specific data sets can substantially deviate from G bar of x. This is what I am going to try and show you with some examples. Why does noise damage GD of x so much? Why does your final hypothesis for specific data sets get heavily damaged due to noise? I'm just going to give some few examples so that you can start understanding, you develop an understanding for the bad effect of noise. Suppose this was your training data. Your training data had these samples. Okay, it's a probabilistic thing. Just happened that these were your training examples. Your final hypothesis given these training examples would be this blue line, and see how far away from the orange line it is, right? I mean, this is substantially different. This is substantially different from this thing, and therefore this hypothesis is going to make substantial errors on this data, right? So your final hypothesis GD of x, if you were given this data set, just these points would be terrible. Similarly, if you are given these, if your training data by some quirk of fate had these points, this would be your final hypothesis. This would be your final hypothesis, which again is a disaster, right? So the point I'm making is that given the specific choice of your data sets, the specific choice of your data set can have a significant influence on the choice of final hypothesis. This is how noise messes up things for you, and this is what leads to higher Eout. Okay, so hopefully the impact of noise, the manner in which it messes up your final hypothesis for a particular data set, all of that is now clear to you. Okay, we've understood what bias and variance are, and we have also put in place the mathematical equations for bias and variance, right? I have written them right here. We also saw how noise enters the equation. What I want to do moving ahead is visualize these ideas with a figure. And this figure is going to help us cement our understanding of what bias and variance are. So let's look at what we have. Let's say we have a target function that I have indicated by a brown dot here. I'm specifying that the brown dot is the target function. And let us say we have a hypothesis set H1 indicated by this blue region right here. The target function is not a part of this hypothesis set H1. Let us say that this blue dot right here is the G1 bar of X, which is the average final hypothesis over the set H1. These black dots are the G's, the final hypotheses for various data sets that you experimented with. Okay, so this blue dot is the average final hypothesis, and the black dots are the final hypothesis for various data sets. As you can imagine, this blue dot, its place in this entire blue region is somewhat close. It's pretty close to the target function. It is not exactly on the periphery because, like we said, it is very close to the best hypothesis in the hypothesis set H1. This difference is because of the nonlinearity that we encountered, but it is sort of in the place which is near the target function, not on the periphery. The distance between the brown dot and the blue dot, is the bias of the hypothesis set H1, right? So this distance is the bias of the hypothesis set H1. The distance between the black dots and the blue dot, their average value would be the variance, because the variance is the GD of X minus G bar of X the whole square. So the square of these distances averaged would be the variance. And like I said, the distance of the brown dot from the blue dot would be the bias of this hypothesis set H1. Now, because the hypothesis set H1 is a limited set, it's a small set, and the target function is not a part of the hypothesis set, the bias distance is large. Okay, the bias distance is large. Because this is a limited hypothesis set, these black dots are fairly close to the blue dot, which is why the variance is smaller. That is what we are indicating over here. Let us draw another hypothesis set H2, which I have indicated in the color green, and G2 bar of X is the average final hypothesis over this set H2. Okay, over this set H2. As you can imagine, the average best hypothesis over H2 is pretty close to your target function. It's pretty close to your target function. However, the variance in this case would be, which would be the average distance square between the black dots and the green dot, is significantly higher. So with a larger hypothesis set, your variance ended up being higher and your bias was pretty less. This is the visualization of what we have been saying earlier. Remember, I mean, just to reiterate, these black dots are the final hypothesis obtained for various data set from when you were using the hypothesis set H2. Okay. So this is a visualization exercise that we've done. This helps you understand what bias and variance are, and this tells you the kind of distances or the kind of the differences, the values of bias and variance that you are likely to encounter in practice. Now, some of you will jump on this diagram and say that I have sort of artificially drawn these black dots. I have artificially drawn these black dots far away in the case of H2, and I have drawn them very near the blue dot in case of H1. So the question that you would have in mind at this time is, why is the variance of a high complexity model higher? That is the number one question that you would probably have in your mind right now. Why have I drawn these black dots far away from these green dots for hypothesis set H2 as compared to H1? I mean, is this just something that I drew, or is there a reason why variance of a high complexity model is higher? Let us try to get an insight into the answer to this question. We are going to do that with some examples. Okay, we are going to do that with examples. We are going to obtain the answer to this question, or at least an insight into this question with some examples. Okay, for the purpose of the next couple of slides, 2-3 slides, I am going to take the wonderful examples that have been stated by Professor Abu Mustafa in his course on machine learning. Okay, it's available on YouTube, and he has provided us with some examples, and I am going to leverage those examples to make our point. Now, the one example that he has provided is an example like this, where the target function is a second order polynomial. A second order polynomial, and you have noisy data with 5 data points. Remember, I mean, now you may say that 5 data points is just too less. You should have a lot more than 5 data points if you are going to do any reasonable exercise. But this example is being chosen to make a point. Okay. Now, let us try using a fourth order polynomial to fit the noisy data. So the blue curve is the target function, which is a second order polynomial, like we said. The black dots may lie on the blue curve or slightly away from the blue curve. There is some noise. So the black dot, the black circles that are indicated here are not exactly on the blue curve because of the noise. And there are 5 of these. And we try to mathematically fit a fourth order polynomial, which is the red curve, into these 5 data points that we have. And if you try to do that exercise, what you end up with is a curve like this. Okay, the red curve is the best fourth order polynomial that fits these 5 data points. And as you can see, the E in is virtually 0, but E out is high. Okay, the E out is high because there is substantial difference between the red curve and the blue curve at various points where, you know, the data points are not present. Okay, so it fits the data points exactly, but the deviation of the fourth order polynomial is substantial. And this is what you would notice if you would actually go through the exercise of fitting a fourth order polynomial in these data points. This is what the good professor has done, and I am using his example over here with credit to make the point. So as you can see, in an effort to fit the noisy data points, your higher order polynomial shows large deviations elsewhere. This is what happens when you try to fit a higher order polynomial. Let's look at a couple of more examples. Again, these examples are from the same course by Professor Abu Mustafa. And let's see what these examples are. The first graph is a noisy low order target. Okay, so these black circles were generated using a low order polynomial, but there was noise in it. So you can see that they sort of deviate from the low order target. And what you tried to do was you tried to fit a second order polynomial into the data, which is the green curve right here, the green curve. And then you tried to fit a 10th order polynomial into the same data. Okay. And what you can see is that the E in this case is 0.05. For the case of the 10th order polynomial is 0.034. E out here is 0.127 and E out over here is actually 9.0. Okay. So what this tells us is that the 10th order polynomial may actually give you a lower E in, but it's going to get destroyed on E out. It's going to give you a substantially larger E out simply because of the nature of the higher order polynomial. Again, as you can see, its behavior in an effort to pass through all the noisy data points, it is going to see a substantial deviation elsewhere, right? It's going to see a substantial deviation elsewhere, as opposed to that the green curve simply tries to sort of pass through the data points as well as it can, and therefore it generalizes a lot better. The in sample error, no doubt the out of sample error is higher, but it is not as high as it is in the case of the 10th order polynomial. You can spend a minute if you like, stop the video over here and go over this diagram once again. So this is what happens when you try to fit a higher order polynomial, and this is what happens with your E out. Now let us take a noiseless high order target. These black dots here, these black circles over here have been generated using a 50th order polynomial. Okay. So they are generated by a 50th order polynomial. And you again tried the same exercise. You tried to fit a second order polynomial into this data, and you tried to fit a 10th order polynomial into this data. And here is what you see. Again, the second order fit is sort of approximate. It tries to do the best job it can. Obviously doesn't do a very impressive job on the samples, but it tries to do whatever it can. On the other hand, the 10th order polynomial, while trying to fit a 50th order polynomial, what happens is that you see substantial deviation. It sort of, there are a lot of peaks and troughs while it tries to fit in this data. This is what happens. So there is a little bit of a, how should I put this? This is a little bit non-intuitive, right? So your target was a 50th order polynomial. It is a noiseless target. So these black points here, these black circles here, which are the data points, have been generated in a noiseless manner with a 50th order polynomial. You would typically intuitively believe that a 10th order polynomial would do a better job of fitting a 50th order polynomial as compared to a second order polynomial, because a 10th order polynomial in your mind is closer to a 50th order polynomial as compared to a second order polynomial. But that is not what you see in terms of E out. In terms of E out, what you will see is that the 10th order polynomial, when you try to fit it into this data, ends up being a disaster. Okay, this is a disaster. Your E out for a second order polynomial was pretty decent, 0.12. Your E out for the 10th order polynomial is very, very high, and the reason is right here. Your E in was extremely low for the 10th order polynomial. So what the 10th order polynomial tried to do is it tried to do an extremely good fit into your data, giving a very, very low E in, but in the process it destroyed the E out. So as you can see, higher order polynomials generally do a pretty poor job of E out when you are trying to either fit noisy data or noiseless high order target data. Now, one way to think about noise is to imagine that the noise is actually being generated by an infinite order target, right? Because There is no pattern to it. It is random. So that is one way of looking at it. So in that sense, noisy target or a noiseless high order target are in some sense the same thing, because a noisy target is essentially a infinite order target, right? So this is the behavior you see when you try to fit polynomials into noisy low order target or noiseless high order target. And right here you see something that is absolutely counterintuitive. Okay. So these are observations based on examples or data that Professor Abu Mustafa has run, and I am trying to refer to them to make the point that he has made elsewhere. Okay, so what is it about high complexity models? We have seen some examples. We asked a question, we saw some examples. What is it about high complexity models that gives rise to this behavior where the variance becomes very large and consequently Eout becomes very large? Okay, now firstly, higher order polynomials have more extrema. This of course we know. Higher number of degrees of freedom or a more complex hypothesis set allows accurate fit of noisy training data, especially when the training data is limited. Okay, and in an effort to accurately fit the training data, there is substantial deviation on out of sample data. Okay. And finally, high complexity models are more sensitive to fluctuations or noise in the training data. So let us go over these points once again, because these are an attempt to explain to you why the variance of more complex hypothesis sets is higher. I am taking the examples of polynomials because we saw the polynomials on the previous slides. But the polynomials, higher order polynomials, are a way to imagine higher complexity hypothesis sets. So let's make the point. In higher complexity models or higher order polynomials, they have more extrema, as we saw. When you have higher number of degrees of freedom, it allows an accurate fit of noisy data, especially when that data is limited. Especially when that data is limited, which is the domain that we are working with. Remember, I put that disclaimer right in the beginning. They allow for an accurate fit of noisy data, and in an effort to accurately fit that noisy training data, there is a substantial deviation on out of sample data. Okay, and it's also observed that these high complexity models are more sensitive to fluctuations or noise in training data. So if you picked a different training sample, the high complexity model or the high order polynomial that you would get would be substantially different. So each data set results in a completely different high complexity model, and that is what gives rise to a higher variance and consequently a higher Eout. Okay. Now let us go back to bias variance and the word trade-off. The word trade-off is often used in the context of bias variance. There is a trade-off in certain sense, but there is not really a trade-off. So let's understand why this word trade-off comes in, and let's understand what's really the case. So we saw these diagrams several slides ago. We looked at underfitting. In underfitting, you had these brown dots which were your training data, and you tried to fit a simple linear model. This was a case of underfitting, and you got a high bias error, low variance error. In the case of overfitting, you tried to fit a polynomial exactly via the noisy data and or through the training points, and you saw that there is a substantial deviation on out of sample. So you said that a low complexity model has high bias and low variance, whereas a high complexity model has low bias and high variance. This is the statement that we had made earlier. Now let us address the question, high complexity and low complexity with respect to what? Okay. We said that, earlier we sort of put aside that question by saying high complexity and low complexity with respect to each other. Okay. But we should probably try to do better than that. I mean, we should try to nail down high complexity and low complexity with respect to what? That is the question that we are going to answer in the next couple of slides. Okay, What we have plotted here is a bias variance curve for a given n. So for a given size of training data for n samples, what we have done is plotted the error on the y-axis against the model complexity. And as we have seen in the previous several slides, as your model complexity goes up, your bias goes down, because the hypotheses that you have start inching closer and closer to your target function, and therefore your bias starts going down. Okay. On the other hand, as we have seen, we've sort of developed an intuition for the in the previous couple of examples, your variance starts going up with model complexity. So this is your bias curve, this is your variance curve, and the total error, the total Eout is going to be something like this. We are going to add the bias and variance, and your Eout curve is therefore going to be what I have indicated with this dotted line right here, sum of bias and variance. I have just indicated that for when the model complexity is low, your hypothesis set is not have complex enough hypothesis to match your observations. And when your model complexity starts becoming high for a given number of training points, attempt to fit the noise causes large variation on out of sample data. So your variance starts shooting up. So this is the nature of the curves for bias and variance for a given n. Now in deep learning, it's observed that after a certain point in time, as your model starts becoming more and more complex, your error starts coming down. That's a region that we are not going to be talking about in this lecture. But in the range of model complexities that we are talking about, your variance is going to increase with model complexity and your bias is going to go down with model complexity. And your overall Eout, which is the sum of bias and variance, is going to exhibit a behavior like this. It's going to have a minima somewhere here at certain complexity. Let us draw this figure in a different way to answer the question, when are you overfitting? So for a given n, if you plot the E in and the Eout, the errors E in and Eout against model complexity, the behavior that you will observe is that E in is going to keep going down as the model complexity increases, because you would start approaching a very close fit of your training samples, and your Eout after reducing will start increasing at a certain point. Okay, will start increasing at a certain point. And this is exactly what we saw in the earlier slide. This is the place where overfitting starts to kick in. So from this point onward, what you are really doing is overfitting the data. Okay, so this is where you're overfitting, this is where you could say you're underfitting, and this is the ideal model complexity for that particular given n. Okay, so this is, from the curves, you know exactly where overfitting is happening. There are practical ways where you can set aside a part of your training data as validation data, and you can estimate Eout on the basis of how your model is performing on the validation data, and that will tell you where you start overfitting. Okay. So there is a way in which you can determine where overfitting is kicking in. You just don't have to talk about, it's no longer vague, high, low, etc. But you can get a concrete idea of the model complexity beyond which your overfitting kicks in. Okay, this is happening for a given n. Now, one assumption in all of this that we need to reiterate is that we are assuming that the learning algorithm is trying to minimize the in-sample error on given endpoints. Very important. This is what we always believed to be the case. But let's reiterate that assumption once again. We are assuming that the learning algorithm is trying to minimize the in-sample error on given endpoints with no regard for what is happening out of sample. Right? I mean, all it has are the training examples. It has a particular training data given to it, and the learning algorithm is doing its job of minimizing the in-sample error, which is why this curve goes down. And when you try to do that, this is the behavior that you see on out of sample data. Beyond a particular point, beyond a certain model complexity, your Eout is going to start going up again. That is when you overfit. Okay. How about increasing n? Now, we made the assumption, we put a disclaimer right in the beginning that n is, you're essentially dealing with insufficient n. You cannot have access to unlimited training data. And that was the premise based on which we studied the earlier several slides. If you are to plot the error against n, let us see what happens. Now, this is again, I am taking an example created by Professor Abu Mustafa in his course. This is an example of a low complexity model. This is an example of a high complexity model. So this is a low complexity model. This is a high complexity model. And when you plot the error Eout and En, these are known as learning curves. Okay, these are known as learning curves, a terminology that you may want to keep in mind. And the learning curves essentially plot Eout and En against n, increasing training data. In the case of a low complexity model, what you observe is that the Eout and En converge. We know that Eout is going to converge to En. We saw that on the basis of on the basis of the VC theory, right? So Eout and En are going to converge, and this convergence will happen at a level somewhere like this. Okay. Whereas for a high complexity model, for lower number of n's, when you are dealing with insufficient n, your Eout is substantially high. But as you start getting more and more training data, your En and Eout will again start to converge, but they will converge at a lot lower level of the error. So if you had higher number of training points, your high complexity model eventually will start doing a better job compared to a low complexity model, right? So that is what these learning curves show us. I have tried to sketch this with a grid on a graph, where on the x-axis I am plotting n, on the y-axis I am plotting the model complexity. Blue colors represent low Eout, red colors represent high Eout, and what I am saying is that for low complexity models you will begin with certain error, and that error may slightly improve as you increase n, but that error is going to sort of stay with you. On the other hand, for high complexity models, you will begin with substantial error. This may become even redder at some point in time as your model complexity goes up, but eventually you will reach a position where you will hit the blue region. Okay, eventually you will reach a position where you will hit the blue region. So I have tried to do this in a 3x3 grid. To explain how n and model complexity together impact your Eout. Okay. What are our takeaways? The first takeaway is that the limited resource that you have is usually the amount of training data. So the amount of training data at your disposal is the limited resource that you have. Noise is unavoidable in real life scenarios, and therefore this limited training data that you have is, you can assume, it's corrupted by noise, because that's unavoidable in real life scenarios. Very important. This is the most important takeaway. choice of the hypothesis set, that means the complexity of the hypothesis set, should be based on the number of training samples you have rather than the complexity of the target function. I'll repeat. Choice of the hypothesis set in terms of its complexity should be based on the number of training samples that you have rather than the complexity of the target function. So it would be very attractive for you to say that, look, my target function is most likely a fairly complex target function. Let me choose a hypothesis set that is of a similar complexity as the target function, and then let me use whatever training samples I have to get the best hypothesis based on those training samples. And if you try to do that, you would be in for a disaster. Your Eout would be very bad. Okay. On the other hand, if you took a more conservative approach, if you said that, look, I have a certain number of training samples and let me choose a hypothesis set that is compatible with those many training samples, regardless of what my target function is, and then let me try to get the best hypothesis from that hypothesis set, you would end up doing a much better job on Eout. Okay. Now, what do I mean by saying a hypothesis set compatible with the number of training examples? Where we had a thumb rule. Remember, we had a thumb rule. It arrived at in the context of the classification problem, etc., etc. We derived it in that context, but that thumb rule still applies, right? So we said that to obtain good performance, your training sample should be about 10x of the VC dimension of your hypothesis set, or the degrees of freedom of your hypothesis set. It's a thumb rule. So if not 10, you could do 8, you could probably do 6, 7, 12, 13, whatever. But that is the ballpark in which you need to operate. You cannot go with a hypothesis set of complexity 100 if you had only 10, if you had only 100 training samples. That you would be in for some pretty bad Eout in that case. So use that rule of thumb. You have some tolerance to play around. I mean, it's a rule of thumb at the end of the day. You could experiment with a little higher complexity, little lower complexity, probably with a little higher complexity, which would give you, you could, if you had number of training samples equal to 200, just to take an example, you could probably experiment with a degrees of freedom equal to 20, 22, 25, etc., so on and so forth, in that ballpark. But don't take it to, degrees of freedom equal to 100, because that will mess you up. So to repeat, very, very, very important takeaway. The choice of the hypothesis set should be based on the number of training examples that you have, rather than your perceived complexity of the target function. Okay, very important. Finally, the learning algorithm should be modified to address the behavior of high complexity models on noisy data. Okay, we have seen this particularly in the example where a 10th order polynomial tried to fit in the data generated noiselessly by a 50th order polynomial, and you saw what a complete disaster it was. And the root cause of that was the fact that your learning algorithm was trying to accurately fit the noisy data, and you got an E in of 10 to the minus 5, if you remember, right? So that is the behavior of the learning algorithm that you need to address. Your learning algorithm should not blindly try to minimize the error on the training samples. That behavior needs to be modified. Right? So what I'm saying is the learning algorithm should be modified to address the behavior of high complexity models on noisy data. That's the other important takeaway. And this is precisely what is going to move us to the next lecture. This is going to be the topic of next lecture, where we will discuss regularization, where we will discuss validation. And this is, this goes back to the motivation. You remember, right, in the second or third slide, I said that the key motivation for studying the bias variance theory was that it will allow us to understand how those blocks deal with each other. Remember that? That's exactly what I'm talking about. Now you are saying that your hypothesis set, instead of looking at the target function, should start looking at the number of training samples you have. Now what we are saying is that the learning algorithm should not blindly try to look at the training data, but it should try to address this behavior of high complexity models that we have seen. So we will talk about regularization, like I said, but now we are talking about the interplay between the blocks. Now we are going to start choosing these blocks so that they work as a team to deliver the best performance of Eout. Okay, so important takeaways. Summary. I mean, we've covered a lot. The takeaways were in fact summary. But let me quickly summarize what we have seen. This has been a long lecture. So let's see what we have actually studied. We have looked at bias and variance. We've studied them at a general high level, understood broadly what they mean. Overfitting also, we got a subjective idea of what overfitting means. We also looked at the mathematical formulation of bias variance. We derived the theory and we derived the BV equation where Eout was equal to bias variance, and we also saw that noise plays a role in that equation, right? That was the mathematical exercise that we went through. We looked at the BV trade-off. We looked at the trade-off. We saw how the bias variance curves look like. We saw that minimum Eout is going to be obtained somewhere in the middle. And we also looked at the learning curves, which were the curves of Eout and in versus n as opposed to model complexity. That brings us to the end of this lecture. And I have some questions for you. Some thought exercises that you should spend time on. And I'm going to give you 4 or 5 questions. So let's see what these questions are. Question 1. Simple one. Create an example of a high bias, high variance hypothesis for a data set. Okay, we've looked at low bias, low variance. Try to manufacture an example of a high bias, high variance hypothesis for a data set. So it's an all-round disaster. Question 2. This was the bias variance curve and the Eout curve that we looked at. And this was our two-dimensional graph of n versus model complexity, where we assigned blue color to low Eout and red color to high Eout. What I want you to do is I created a 3x3 grid. And I selected the colors sort of approximately. Selected the colors sort of approximately. What I want you to do is to create exactly this grid, but a 5x5 grid. So 25 squares in all. And I want you to carefully select the color of each of the squares in this grid. So 25 different colors, where deeper shade of blue represents lower and lower Eout, deeper shade of red represents higher and higher Eout, and I want each of those 25 squares to have a different color. That will completely help you understand the behavior of model complexity versus n in influencing Eout. So go over this exercise. A simpler way of asking that question, I mean, if you were not up for the exercise of coloring 25 squares, a simpler exercise would be to answer the question, how do these BV curves move with increasing n? So these curves were for a specific n. If I were to increase the n, how would these curves move? Okay, but if you have some time, if you are willing to invest the time and develop a very, very good understanding, I would encourage you to create this 25 square 5x5 grid and make sure that each square in that grid is colored with a different shade of purple, blue, red, etc. That's question number 2. This will take some time. Question 3. Interesting. Why did we not bring up noise when talking of the PAC theory? Remember, the PAC theory said that Eout is less than In plus a quantity that depended on delta N and the VC dimension. We did not bring up noise over there. Can you guess why we did not bring it up there? Maybe we just forgot. Is that the reason? Or is there another reason for not bringing up noise when talking of the PAC theory? Question 4. Okay, we assumed this. I said we would leave that as an exercise. Go through that exercise mathematically of replacing f with f plus epsilon, where epsilon is a random variable with zero expected value, with zero mean, and variance equal to sigma square. Epsilon is a random variable that is independent of the other variables. Make those assumptions and actually show that this equation holds. We assumed this. I want you to actually go through this exercise. Not very hard. Okay, that's question 4. Well, that's it. Those are the only questions I had. Do spend time on those. And this has been a long lecture. It's an important theoretical lecture. Thank you for spending the time. I have already told you what the next lecture is going to be about. It's going to be about regularization, about validation, etc. And I look forward to seeing you for the next lecture. Thank you very much.